So thank you for the presentation. My name is Elisa Fazzari. I'm a PhD student from Sapienza University of Rome. And it's a great pleasure to talk to you and share my recent work that is in collaboration with Maria Giovanna Dainotti and my two supervisors that are Giovanni Montani and Alessandro Melchiorri. And my work is about the effective running Hubble constant in type 1a supernovae as a marker for the dark energy nature. So first of all, let me start with a brief recap of our latest results from cosmological surveys. So from the CDRG results, we know that it's capable of measuring these three types of observables, and in particular, we can constrain the product between the H0 and the southern horizon and omega matter. So if we consider a flat Lambda CDM model, what we see is that the DESI alone data and CMB have a 2.3 sigma tension between these results. And what about an evolutionary dark energy model? From type 1a supernovae, we know from the Pantheon Plus results that if we assume a CPL parameterization, so an evolutionary dark energy scenario, we have these two parameters that are quite compatible with a cosmological constant scenario. So we don't have evidence for a evolutionary dark energy scenario. On the other hand, if we consider the year 5 results, we see that we have a deviation from a cosmological constant scenario, but if we look at Bayesian factor, we have a preference for the flat Lambda CDM model. So coming back to these results, we know that this tension can be alleviated for the first time with an evolutionary dark energy scenario. And moreover, we see that for the first time, an evolutionary dark energy scenario is preferred both with only DESI and type 1a supernovae, and also with DESI plus CMB plus supernovae. So our main question for our work is, are supernovae alone really enable to discriminate the presence of evolutionary dark energy in supernovae and discriminate the nature of this dark energy? So let me begin with the theory part. So we defined a new diagnostic tool that is quite similar to that one defined in the supporting paper of DESI. And we can start defining the Hubble parameter as this coefficient times the Hubble rate parameter of the Lambda CDM model. And in particular, we can reformulate this effective running Hubble constant as the product between the H0 and the fraction between this Hubble rate parameter of a modified cosmological model, and this one that is in the Lambda CDM model. So this function is able to discriminate between different models that are different from the Lambda CDM. So we can see that if we consider some example, the most naive is the Lambda CDM, we have that this function is exactly equal to the H0. And if we consider a dark energy with a W constant, we get this function. And for a CPL parameterization, we have this more complex function. So if we plot this function fixing H0 and omega matter, and we consider different value of W, we see that in blue shapes, we have this function with the slope that is positive. It indicates a quintessence dark energy, whereas in the red shapes, we have the phantom dark energy. So this, in this sense, this function is able to discriminate in principle between these two natures. And this is valid also for the W0 WR CDM model, and this is why if we consider the first derivative of this function, we see that it depends uniquely from this term. So if we have a W naught that is higher than -1, we have the increasing trend of this function, whereas if we have phantom dark energy, the function initially decreases. And this is also true for DESI results. If we consider DESI plus CMB plus different types of supernovae, we see that at the beginning, this function is increasing, so the slope is positive. It indicates quintessence dark energy, whereas when there is a maximum, so a phantom crossing, and then when it decreases, there is an indication for phantom dark energy. So in our work, we will test two phenomenological models that are the WCDM model and this reduced CPL model where we impose W0 equal to WA, since our data are not able to constrain two parameters. So these are the formula. And we consider a third model that is a new theoretical model labeled as DDA. And we have an evolutionary dark energy that is created by the variation of cosmological gravitational field. In particular, we consider a particle creation mechanism. So we have this modified continuity equation where we have an additional pressure term that is negative, and this is in particular the phenomenological constant particle creation rate. So if we consider these two equations, we can obtain the final continuity equation for dark energy. And furthermore, we consider this other theoretical constraint that is to be sure to maintain the distance moduli relation until redshift equals 0. So in this way, we impose that the acceleration parameter of our model is equal to that one from the Lambda CDM. And this way, we are able to constrain, to fix a free parameter of the model, and we have only one added free parameter that is W. So in the end, we have the Hubble rate parameter for the model. This is the part of the dark energy, and we can write from this continuity equation W, an effective W, and we see that it depends on the redshift, so we have an evolutionary dark energy. And this is the function of the effective running Hubble constant. So to summarize, these are the three models that we are going to test, and these are the two models that we use to compare the three dark energy models. The first one is, of course, the Lambda CDM model, and the second one is the power law, that is a function that was used from Maria Giovanna Denotti in her works, and it indicates, it is used in astrophysics to see if there is an evolution with the redshift in the function. So in this work, we are testing these three functions with the binned supernovae sample that are the Pantheon binned for this first work, and the master binned supernovae that are a collection of the CR5, Pantheon Plus, and Pantheon JLA without duplicates. And in particular, the bin data set is composed by 20 bins, and in each bin we have an H0 inferred and also an omega matter. And we consider the case with equipopulated supernovae. So these are the priors used for the first part of the test, and are the same used to obtain the bin data samples to be consistent. And we inferred the three parameters of the model that are H0, omega matter, and the W parameter for dark energy with performing an MCMC through Kubaya, and we adopted this total chi-squared. And in particular, we used a new code that is in preparation and developed with William and Jerry, and it's particularly useful to test late-time modified cosmological models, and in particular for dark energy and Hubble tension. So what we got from this analysis is that if we see The first and the third case is the WCDM model with the binned supernovae data, and we compare the binned supernovae data with the full supernova sample, and we see that the constraints on W are narrower compared to the one from the full supernovae data that are broader. And this is valid also for other two models. And these are the results in particular, and we can see, especially for the Pantheon bin dataset and for the WCDM and the last model, that we are able to constrain in 1 sigma the nature of the dark energy. So in particular, in this case, we have phantom dark energy, and also in this case. But if we look at the log of the Bayesian factor, we can compare these models, and we see that both for master and Pantheon samples, we have that WCDM and DDA model perform better compared to the evolutionary dark energy model. And lastly, we see that the power law function is preferred compared to the Lambda CDM model. And finally, we tested these 3 models also with the background sources. In particular, we adopted the Pantheon and master sample, and DESI, DRDU data with a calibration on the southern horizon on Planck constraint, and also the cosmic chronometers. And what we got is that the statistical uncertainties on the W parameter are much larger, quite larger compared to that one obtained in the binned case of supernovae. And we can see also that we don't have, in some cases, a discrimination in 1 sigma from phantom and quintessence dark energy. So these are the contour plots of the results. In red, we have the master plus DESI plus cosmic chronometers, and in purple, the Pantheon plus DESI plus cosmic chronometer results. And this is the reconstruction of our fitted models with data. And we see that for the redusty PL model, we have initially an increasing of, so a positive slope of this function. In fact, we have a quintessence dark energy, and then it decreases. And this one in magenta is the power law model that is preferred from data. And this is the reconstruction of the equation of state for the dark energy. And again, we see that we have initially for the redusty PL model a quintessence trend, then a phantom crossing around a redshift of 0.2. And the blue one is a WCDM model that it's a phantom. And in green, there is the DDA model, so the new model, that is initially consistent with a cosmological constant scenario, because we impose the deceleration parameter equal to that one in the Lambda CDM model, but then it prefers phantom nature. So in conclusion, we have that this H0 of zeta function is a useful tool. So it's a diagnostic tool that can, in principle, able to discriminate between dark energy, quintessence, or phantom nature. And then from the test of the models, we see that the bin data prefers phantom dark energy scenario. And lastly, the power law and Lambda CDM emerge as the most favored parameterization from type 1A supernovae. So that's all. Thank you for the attention.
Thank you for your talk. Can I take your questions?
Hi, thank you. Thank you for your talk. Sorry for the question. Maybe I'm not an expert, but at the beginning, you said at some point that you had to fix H0 to 70. And I would like to know why, and why you have to fix it, and why 70. Thank you.
Thank you for the question. And yeah, I said at the beginning that
Yes.
here.
Yes, here. Yes.
Okay. We fixed H0 equal to 70 because in the Pantheon and master sample bin data, we use these data that are calibrated with these H0 values. So we fixed it, but in general, for our scope, it's not important the point where it starts this curve, because we want only to reveal qualitatively if there is an evidence for dark energy in general and discriminate between the nature. And this is also true for the omega matter, because we can see here. Yeah, we plotted the curves fixing H0 and W, and we see that omega matter doesn't affect the qualitative trend of the curve. So it's true also for quintessence and phantom cases.
Thank you for your talk.